Hello, welcome back, and this is Fahad, and this week we'll talk about forced hot air system design for a heating system. We'll start by first explaining how to measure the quantities that you have to introduce into the room to heat or cool the room, and that is done by converting BTUs into CFM. And CFM here is cubic foot per minute. And we'll talk about different type of motors and drives, various duct system available, and finally noise control, which is very important when it comes to forced hot air. So our here is how do we convert CFM to CFM from BTU. So that's very simple. You can use this equation, and you will go to each room. You already have your BTU for each room. You divide that by 1.08, which is a constant. This is a constant, given the circumstances. It's not a constant, but for our case, it's a constant. And it's the air heat capacity. This is heat, not T. Heat capacity of air. And delta T, so delta T is here. And this is stays as is, 1.08. And temperature difference is the desired room temperature. Let's say we want to keep the room at 75, and the difference between the incoming air temperature. Of course, you're going to get the difference, and you have to have it in positive number. So what is the incoming air temperature? Could be 100, could be 85, could be 90. Let's say it's 90 degrees, so that will give you 25, and that will be different based on your design. So this is what you actually want, and this is what you assume as your hot air capacity. So usually it's 90 or 100. So you can put a number for your project and assume this is going to be your system. This will also vary based on the fuel you're burning, the efficiency of the system, and duct work. So based on that, you can get the temperature. If you're burning oil or gas, probably have hotter temperature than if you're using a heat pump. So this will depend on your heat source, so it can vary, and this is something you pick. So for your project, you can put 90 or 100. That's whatever you find is reasonable. Make sure you have a positive number here, and this is how you convert for each room the BTU into CFM. Some notes we have to think about when we do sizing for duct. Again, it's very involved work, and it requires some experience, but at least you have the cliff notes here of what you have to do. So air velocity should be between 900 to 700 to 900 foot per minute. This is foot per minute, and we want frictional losses between 0.08 and 0.1, and this is the water gauge losses. Again, we said like the pressure losses is done also in inches of water, so we want this much per 100 foot of duct work, and we will talk about this calculation, but there are some calculators that does that for you, and there are charts. The reason we don't want the air to go faster is because if it goes faster, it will encounter more friction. So this is something we have to keep in mind, and also we have to keep that the flow rate, how much quantity of air you will be putting into the room, is dependent on the area of the register and the velocity of air. The faster, so again, area times velocity. This is my velocity over here. So if the velocity increase, the flow rate will increase. And if the area increase, also the flow rate will increase, and vice versa. If you want the same flow rate and you decrease the area, you will increase the velocity. But if you exceed this number, you start having some noise. Aspect ratio for the register is no more than 3:1. So that's for register, which is if this is my duct, this is my opening here. I have this my register. You want to be 3:1 foot or 6:2, which is really huge, or you can go 1.5 by 0.3 per foot. So you want to keep that aspect ratio for some static reasons, also for flow rate reasons. So this is an example of a house being converted from BTU to CFM, and that can tell you many things actually. Let's look for this in heating if I want to reverse calculate that and see what they use for heating. So I have 100 BTU was turned into 300 CFM, so we use the higher number, of course, not for cooling. You size for heating, not for cooling, because heating is more BTU than cooling. So 18,000 over, we said 1.08, and we get 300 CFM. I want to see what is my delta T. So what I would do is I will multiply that 300 equal and divide 1800 over. So here I got a delta T. If I solve for delta T, I'll get delta T of 60 degrees. So probably we have the room at 70, and my temperature will be 70 plus 30 is 130 degrees. That's very hot. So, and my delta T here became 60 degrees based on this calculation, which is pretty high temperature. But again, this is how it's done. So what you will do in your project, you will plug in your BTUs, plug in your delta T, desired delta T, and plug in your heat capacity for air, and you will get your CFM here. Okay. Let's talk about the other topic, which is conditioning the air. So we call it air conditioner because it does not only add heat, it does other things. So we can do heating and cooling, particle removals like dust. We also do moisture control, which we can add humidity or dehumidify the air. Whenever you do cooling, usually there is a dehumidifying factor, and you always need to have a condensation pump because you will collect some water. Also, some models do some ionization, which is, I think it's a gimmick, but again, it's going to be an option. Ionization is releasing some electrical charges in air, hoping that those ionized particles will stick into a positively charged plate. It does work. I think it was very common at some point, then they stopped doing that. So we talk about cooling oil, also a heating device that will go into your hot air system on top of the furnace, and we can add humidity device to clean the air. So if you look at our furnace here, over here, this is your furnace, this is your heat exchanger, and this is your cooling coil. They call it sometimes the A coil because it looks like an A here. That's going to be your evaporator. The filter usually comes in here, and the humidifier goes into the duct in the top here. There's a small little mesh that add moisture to the air. So we also have to know that the forced air system does always use the air over and over again. So at some point you have to design a way to introduce some new air to the system. Otherwise, the air will keep circulating and their quality will go down. So we can always have mechanical mean to introduce fresh air. And think of your AC in the car. There's a vent. Once you open the vent, the negative pressure inside the duct will pull in some air from the outside and exchange the air inside the cabin. So the same thing will happen. Some air coming inside while you circulate the air. And again, this is the air handling unit. This is where you have your supply air duct to the house. This is the incoming air. The air goes through the furnace. If the heat exchanger here is off, probably you have your A coil in here, and it will provide you some cool air. So you can cool and heat in the same air handle. So we have to deliver the correct air quantity to the house. By quantity we mean volume, so that's why we calculate volume flow rate. Different spaces of course require different quantity. That's given based on the BTU, and the same structure sometimes might have different cooling requirement. That's also based on the BTU for that space. Components of the forced air system: we need a blower motor that goes into the air handling unit, air supply system coming from the house itself, or also a combination from the house and inside, return air system coming from the house, and we need grills and registers that will act like your dispenser for the hot air or cold air inside the room. Ideally, you don't want the occupants to know the system is on or off. This is how soft you want the noise to be, but that's not always the case. But we strive to make it as quiet as possible and as effective as possible. This is the distribution of an air system. Again, this is my air handling unit, and these are my registers. This here is my blower motor. Looks like a squirrel cage, and to push the air through. It is going to be very loud. That's why we sometimes put it in the basement or in the attic so we don't hear it. And we just want the air to move slowly and smoothly through these ducts and go outside. This is called the supply register, and we said the aspect ratio should be 3:1 ideally. The blower, it adds pressure. That's your blower motor. It acts like a big inducer fan that will blow out pressure inside the main duct, and it will branch into small little ducts. And this is another general rule that for 400 CFM we will have 1 ton of refrigeration, which is 12,000 BTUs. So this is the equipment that you would like to have based on the ideal flow rate again, and it's not always achievable, but it's kind of the best practice number. Again, the pressure inside the duct is measured by water gauge, and if you use a manometer to go and check your pressure inside the duct, it will tell you what is the velocity pressure going inside the duct. And that's important because using the velocity you will measuring the pressure, you can use that pressure to velocity pressure to convert into air velocity. So if you have a velometer, you can, it looks like a little fan, a tool with a fan in it that will give you the speed, the velocity in here. But if you don't, you can use a manometer and calculate the pressure to calculate the airflow. So again, water manometer. Why do we need a manometer? Because a manometer is very small. It has a probe that goes through a small hole inside the tube and can measure the velocity doing that. If you use the fan equipment, it's a little bit too invasive and too big, and it's really hard to get inside the duct to know what is the velocity of the air inside the duct. This is an example of a Venturi fan. It's not an inducer fan. So if you notice that little squirrel cage fan in the blower motor might not be enough to provide enough pressure throughout the duct, so you might need some propeller fans around inside the duct to add some pressure to it as we go along. And again, we have to be considerate of the sound effect that has on the duct. The duct is going to be hollow and to have a lot of echo, especially if it's not insulated. So you don't want the system to be too loud. So there's either a squirrel cage fan or a centrifugal fan, different kind of fan used in the duct system. This just like describe different types of fans that we can have inside. It's an example of the squirrel cage fan. It provides a lot of pressure, and the volume that's dispensed by that fan compared to the noise is very efficient, and those also can fit in very small tight spaces. We can also have squirrel cage fans goes inside the duct along with the motor, and probably you did that in the refrigeration course. You did replacing the fan, and you can see how it is a little bit inconvenient, but we need those fans to act like pumps to push the air around the duct. Again, the drive, there are two types, either direct drive where you have the motor connected directly to a fan, that's direct drive. Indirect drive is when you have the motor by itself connected to a pulley, and the pulley is connected to a fan. They have a belt between them. That's make things a little bit more convenient to be able to change the motor without getting inside to the fan which is inside the duct. This is the belt drive. and this is the squirrel cage drive with a direct drive. Okay, I will pause here and post the second video, which will describe supply duct system and different types of duct we have for forced air.